Hello everyone. In the previous class, we have discussed about the other important effects, specifications for switching, and some other important effects in which we have listed drift in the base region, base narrowing, and avalanche breakdown. Out of that, we have covered drift in the base region. In today's class, we are going to discuss the base narrowing and avalanche breakdown. So the figure shows the effect of the base narrowing on the characteristics of P plus N P plus transistor, that is P side of the transistor, that is emitter as well as the collector, both are heavily doped, and base, that is N, is lightly doped. So the figure A, there are two figures here. The figure A shows the decrease in the effective base width as the reverse bias on the collector junction is increased. And the figure B shows the common emitter characteristics, showing the increase in the IC with increased collector voltage. So here in the figure B, the black lines that indicates the extrapolation of a curve to the early voltage VA, that is indicated there. So if the base region is lightly doped, the depletion region at the reverse biased collector junction can extend significantly into the N-type base region. So observe the figure carefully. Figure A, as shown in the figure A, so we know that the emitter and the collector both are heavily doped. They are P type and they are heavily doped, whereas base N is lightly doped. So if the base region is lightly doped, then the depletion region at the reverse biased collector junction can extend into the N-type base region. So as the collector voltage is increased, the space charge region or the space charge layer takes up more of the metallurgical width, the base LB, and because of this, the effective base width WB is decreased. So observe the figure. So here, as the collector voltage is increased, the space charge layer is going to take up more of the metallurgical width of the base LB, and because of this, the resulting effective base width WB is going to decrease. So the decrease in the WB causes beta to increase. So because of this, the collector current IC increases with collector voltage rather than staying constant as predicted from the simple treatment. So here the slope indicates, slope is introduced here by the early effect. It is going to be almost linear with the collector current IC, and the common emitter characteristics extrapolate to an intersection with the axis VA, and it is called the early voltage. So for P plus N P plus device, so as we are seeing this figure, so it's a P plus N P plus device. So in a figure A, so we can approximate the length L of the collector junction depletion region in the N material, and it is given by L is equal to 2 epsilon VBC by QND to the raised to half. So if the reverse bias on the collector junction is increased for enough, it is possible to decrease WB. That is, the effective base width is going to decrease to the extent that the collector depression region essentially going to fill the entire base. So in this punch through condition, so this is called as the punch through. In this punch through condition, holes are going to swept directly from the emitter region to the collector here. Holes which are in the emitter region are directly swept to the collector region, so that the transistor action is going to lost. So punch through is a breakdown effect. Here punch through, it is nothing but it is a breakdown effect that is generally avoided in the circuit design. So remember here, punch through must be avoided in any of the circuit design. So in most cases, what happens is avalanche breakdown of the collector junction occurs before punch through is reached. So this is about base narrowing. The term base narrowing means base, the terminal base in between the emitter and the collector is going to be narrow. Its width is going to decrease. So that is nothing but called as base narrowing. You can observe that one in the figure. So base is going to be narrowed. So the width of the base, the effective width of the base is decreased. That is LB minus L. Next one is the avalanche breakdown. So this is the last topic of the module, avalanche breakdown. The figure shows the avalanche breakdown in a transistor. So here also there are two figures, figure A and figure B. Figure A is the common base transistor and figure B is the common emitter configuration. Common base transistor configuration and common emitter configuration. So figure A indicates the collector current increases sharply at a well-defined breakdown voltage BVCBO. So that BVCBO is nothing but a breakdown voltage at the collector common base configuration. So in a figure A, the collector current increases sharply at a well-defined breakdown voltage BVCBO. So observe the arrow mark that is shown here, BVCBO. So here the collector current increases very sharply at BVCBO, that is for the common base configuration. Observe figure B. For the common emitter case, however, there is a strong influence of a carrier multiplication over a fairly broad range of collector voltage. So further, the breakdown voltage in a common emitter case, that is indicated as BVCEO, that is breakdown voltage in the common emitter configuration, is significantly smaller than the other one, that is BVCBO. So we can understand these effects by considering breakdown for the condition IE is equal to 0 in the common base case and for IB is equal to 0 in the common emitter case. Both are indicated in the figures. IE is equal to 0 in the figure A and IB is equal to 0 in the figure B. So these conditions are implied by the O in the subscripts of the BVCEO and BVCBO. So observe there O is nothing but is I is equal to 0 in first case and IB is equal to 0 in the second case. So that is the O is the subscript here, that is used as collector current, emitter current is 0 and base current is 0 respectively in figure A and figure B. So in each case the terminal current IC is the current that is entering the collector depletion region multiplied by the factor M. So including multiplication due to impact ionization. So here IC is equal to alpha N into IE plus ICO into M. So that is equal to alpha N IE plus ICO into 1 upon 1 minus VBC by BVCBO raised to N. So for the limiting common base case of I equal to 0, the collector current IC is simply M into ICO and breakdown voltage is well defined as in an isolated junction. So here the term BVCBO, it is going to signify the collector junction breakdown voltage in the common base with the emitter open. So here BVCBO is nothing but it is a collector junction breakdown voltage. BV stands for breakdown voltage. So for the collector junction breakdown voltage in the common base, CB stands for common base with the emitter open, that is IE equal to 0. So in the common emitter case, the situation is somewhat more complicated here. IB is equal to 0 and therefore IC equal to IE. So IC is equal to M into ICO divided by 1 minus M into alpha N. So in this case, the current increases indefinitely when M into alpha N approaches unity. So by contrast, M must approach infinity in the common base before BVCBO is reached. So observe the equation carefully here. Since alpha N is close to unity in most of the transistors, M need be only slightly larger than unity. So since a V is close to unity in most transistors, M need be only slightly larger than unity to approach breakdown. So avalanche multiplication therefore dominates the current in a common emitter transistor well below the breakdown voltage of the isolated collector junction. The sustaining voltage for avalanching in the common emitter case BVCEO is therefore smaller than the BVCBO. When an ionizing collision occurs in the collector junction depletion region, a secondary hole and electrons are created here. Secondary hole and electron are created. The primary and secondary holes are swept into the collector in a PNP. But the electron is swept into the base by the junction field. So therefore, the supply of electrons to the base is increased. And from our charge control analysis, we conclude that hole junction at the emitter must increase to maintain space charge neutrality. So this is nothing but a regenerative process. So here an increased injection of holes from the emitter causes an increased multiplication current at the collector junction. So this is in turn increases the rate at which a secondary electrons are swept into the base, calling for more hole injection. Because of this regenerative effect, it is easy to understand why the multiplication factor m need only slightly greater than unity to start the avalanching process. So this is about avalanche breakdown. Thank you for watching the video.